In this video, I will introduce some hypotheses on generalization of deep neural networks. Right. So there are some papers on learning rate. It's very related to the generalization error of the neural network. Why? Essentially, the training loss function of deep neural network is totally non-convex and there are many local optima. So there are many local optima like this. Okay, this is just a rough idea of why learning rate is related to the generalization error. So this curve actually can be very far from the real loss function curve of deep neural network. But to make simple to explain, I will assume there is only one single parameter theta, and the loss value function looks like this. Okay, so this is training error curve, and in terms of training error, of course this point is the optimal point, and when you want to minimize the training error, you have to find this point. But the most important thing is not training error, but test error. Okay, we have to find some nice point that can minimize or that can make very small test error. Okay, so one hypothesis of deep neural network for the connection between training error and the test error is when you find a very wide area, you generally have small generalization error. When you have very narrow valley, you usually have very huge generalization error. This is because the test error, we usually look at some difference data point, so the loss function will different, but not entirely, but little, because the main features. So when we train some image classification task, then the test also image classification task with the same type of pictures or paintings. So usually the test loss curve looks like a training loss curve, but real different. So there might be some shift and some distortion from the training loss value, but the valley is wide, there are many overlap. And when valley is very narrow, essentially there is almost no overlap. So when you find this point as the best training loss point, in terms of test error, so let's say the blue curve is test error, this is very bad, right? But when you find the local optima with a wide valley, essentially you usually have very nice test error as well. The generalization error gap of a wide valley usually very nice. So some people claim that we have to find a local optima belong to wide valley, not the narrow valley. Okay. So this hypothesis can explain why we have to set some large learning rate instead of tiny learning rate. Okay. When you use some sufficiently large learning rate, before enters a very narrow valley, because here the slope is huge, when you have a sufficiently large learning rate, the next update will go to here. This point as well. When you here, then the gradient point is the slope is very huge, so with some sufficiently large step size, your next position will be somewhere here. Okay, so you can escape from the narrow valley, and you can go to some wide area, which can make very nice generalization property. So people believe that, or this is not rigorously proved, but just conjecture. When the learning rate is high, when learning rate is high, you have better generalization here. And usually people believe that with a high learning rate, we usually learn very simple, easy example, which can generalize well. On the other hand, if you decrease the learning rate, your generalization behavior can be worsened. And but you have to think this as well. When the learning rate is too high, it never converges. It always oscillates. Okay. So you have to decrease the learning rate at some point to have very nice point. So when you have a learning rate is very large, even in this wide area, your update never converges to the local optima. When you decrease the learning rate, on the other hand, you can very carefully update your next position so you can converge to the local optima. Okay. Learning rate. So that's why we need some learning rate scheduler. Essentially, at the first page, we have to use some large enough learning rate so that we can escape from the narrow valley. After sufficient amount of iteration, we have to change the learning rate to small values so that we can converge to local optima. Okay. So this is one hypothesis. Okay. And so with this explanation, we can explain the why stochastic gradient descent algorithm perform very well with deep learning applications. Essentially, the stochastic gradient descent algorithm, at each iteration, we look at different data point. At t iteration, at t plus 1 iteration, we look at different data point. So let's say dt is the data point we sampled for the tth iteration. Let's say dt plus 1 is the data point for the t plus 1's update. Essentially, every time there is no overlap between dt and dt plus 1. Okay. Then we can think this stochastic gradient descent update rule as this. This is kind of training. This is kind of test. The data point for t plus 1 is, again, training. And t plus 1, 2 is test for the training of t plus 1. Right? So this iterative update rule is kind of training test, training test, training test. And each update is kind of update so that we minimize test error. Right? So because this update rule is kind of training test, training test, training test. When it comes to this loss function graph, each time we will see different loss function, right? Because we look at some different loss value, right? And when you use different data point for each iterations, usually we can expect that, maybe we can expect that in the end, the solution will be some area, will be in some area where all data points have good training value. And which usually, in that area, usually we can have very nice test error. Because for every subsample data point, we can expect very nice training error. When you sample new data point, you still can expect very nice error, which means we can expect very nice test error. Right? So many people believe that, although this is not rigorously shown, the stochastic gradient descent algorithm itself is very nice regularization technique for your deep learning algorithm.